you start the recording? Okay, welcome everyone to the final eCHT of this fall. We're happy to have Tom Bachmann, who's going to tell us about motivic cohomology of motivic Eilenberg-MacLane spaces.
Okay, well, thank you very much for inviting me. Right, okay, first order of business, I have to tell you this is all work in progress. And I apologize, it has been in progress for a while, and it's probably going to be progressing for a while longer, but I'm also pretty confident that what I'm going to tell you, I'm very confident it's all correct. Yeah, okay, so that's just a warning. And also I should say everything is joined with Mike Hopkins. Oops, it's not quite how you spell it. So I should, of course, always remember to say his name. Maybe I might forget, in which case, you know, my fault. Okay, anyway, so with the bureaucracy out of the way, I guess I want to begin by telling you a little bit about motivic cohomology. I mean, it's probably fairly safe, I would guess, to assume. Oh, can everyone see my screen? Someone can't see my screen, apparently. Okay, good. Okay, so it seems fairly safe to me to assume that you know what motivic cohomology is, sort of, but let me very quickly remind you. So we're working over a field K. And then you can have this cohomology theory for smooth schemes, right? So for X in smooth K, so this is some smooth K scheme. For example, K could be the complex numbers, and it's already an interesting result that I want to tell you. So this is some smooth complex variety. And then one has these groups, right? And they're defined by various people. So maybe Bloch is the name, which is relevant. Levine, Wygotsky, of course, and so on. And so they dreamt up this cohomology, they dreamt up and turned into reality this cohomology theory. So they construct, and I'm not going to tell you how they construct it, it doesn't really matter for what I'm going to do, but they construct these motivic cohomology groups. So what are they? I mean, so you take two integers, I and j, and you can have a group of coefficients, which can be any abelian group A. I mean, almost all of the time, it will be just Z or Z mod P for me. So this will be some abelian group. And here I and j are integers. A is also some abelian group of coefficients. So it's just like normal cohomology, just to have a second index. And you, you stick in a smooth variety and not a topological space. And so these can be, or are, I suppose, to me, quite mysterious, but there are some examples of groups which one understands. So for example, you have H21 of X with the Z coefficients. This is also known as the Picard group of X. So this is the group of line bundles up to isomorphism. And more generally, one knows that H2n, n of X with Z coefficients, this is the so-called Chow group. So it doesn't really matter if you don't know what the Chow group is, but this is sometimes motivic cohomology groups are called higher Chow groups, and the reason is this. So you start with these, and then you build in some more groups to make a cohomology theory. And also there's this famous result of Totaro, I guess, HNN of, if I stick in the base field with the integers, then you get something called Milnor K theory. Again, if you don't know what this is, it doesn't really matter, but I'm just trying to point out that in general, these groups are quite mysterious. They're related in somehow to K theory, which I guess is also quite mysterious. But at least in some edge cases, we can compute something about this. That's the point of the business. And so, as I said, I mean, I'm not going to explain to you exactly how they build these groups, but certainly what they do is they write down some complex, and the cohomology groups of that complex, that's what motivic cohomology is. So in fact, let's say for J and Z, there is a complex, the motivic complex of X. So I might denote it something like Z round brackets J of X, such that you can express the motivic cohomology groups in terms of this, right? So hij of x with coefficients in A. How do you get it? Well, you take the ith cohomology group of this complex zj of x. And well, I mean, if you want to stick in some coefficients, then you have to tensor with A. And maybe to be on the safe side, I put an L over here. But of course, everyone knows that all tensor products are derived. So anyway, so that, yeah, so there is this complex and there are various recipes. Yeah, I mean, Bloch had some initial definition of how to do this, and maybe Voivodsky has some other complex, and then he proves that they're quasi-isomorphic, so it doesn't really matter which one you use. But in any case, you can find this thing. And I mean, one of the good things about Voivodsky's complex, which are very non-obvious about Bloch's complex, is that this is in fact completely functorial in X. This is functorial in X. And so what this means is that you can view this as a pre-sheaf of complexes if you want. So we obtain a pre-sheaf, let's say, of spaces. I will know it might be denoted by K, A round brackets J, comma I. And this will be some pre-sheaf on smooth schemes. And it's just defined by K, A, J, comma I. If I want to evaluate it on X, well, I take this motivic complex, ZJ. I guess I should better tensor it with A here. And then I should shift it correctly. So I think I should put some I here. And then I make it into a space, so I just write infinite loop space of this complex. And this pre-sheaf is what's called the motivic Eilenberg-MacLane space. MacLane space. Okay. So that's somehow the guy that we want to determine the cohomology of. Let me point out that this has some good properties in the sort of category of pre-sheafs of spaces, which is that if you look at homotopy classes of maps from X, which I just view as a representable pre-sheaf of spaces, into this Eilenberg-MacLane space, then of course you get, that's just how representable pre-sheafs work, the motivic cohomology group, right? So this is going to be Hij, X, A. It's a bit tautological if you work in these pre-sheaf categories, but okay, so that's true. And the other thing that I want to point out is that if you take any, so maybe this is another NB. So if F in pre-sheaf on smooth K, right? So take any pre-sheaf that you want whatsoever, right? Then we can just define Hij, XA as, well, is just going to be homotopy classes of maps from F into this K, AJ, I. And in particular, right, so this way I can define motivic cohomology of any pre-sheaf of spaces. For example, I can take motivic cohomology of this pre-sheaf of spaces, which is the motivic Eilenberg-MacLane space, right? So with these preparations, it totally makes sense to ask what are the cohomology groups of the motivic Eilenberg-MacLane space? And that's the goal of my talk, is to explain what they are. All right, any questions so far?
In the last line, oh yeah, should that be an F instead of X?
There should definitely be an F there. Yes, sorry about that. Like this. Thanks. Okay. And so in principle, you could ask, what is the cohomology of an Eilenberg-MacLane space with coefficients in some any A, and then you can put here any B, and so on and so forth. So there are a lot of related questions that you can ask. And so various of these can be answered, but from now on, for the purposes of this talk, I will put A equals the field with two numbers, elements. From now on, A equals F2. So I'm only going to consider this case. So you can do FP for any prime P, which is invertible in your field. Yeah, so maybe I'm going to assume that 1/2 is okay. And then the answers, I mean, as usual in topology, you can do the odd primes or you can do two, and the answers are a little bit different, but they're completely, I mean, we have completely analogous results. I just want to explain the F2 case because it's somehow the easiest. So you can also do something like Z mod P to the N coefficients or Z coefficients, and then it gets more difficult. But anyway, so I'm going to explain the case of F2 coefficients everywhere. Okay, so the answer for the cohomology will be expressed in terms of cohomology operations. So I will just very quickly remind you about those. So we can crudely define cohomology operations for now. So a cohomology operation this is just a natural transformation. So it's a natural transformation. Let's say from hij blank comma a, well, I guess a is f2, but to some h, some other thing that you want. Let me put maybe I prime comma j prime blank comma a. And this should be defined where if I stick in any presheaf of spaces f. Defined so on all presheaps. Okay, so oftentimes these operations will come from doing some specific thing with the sort of presheaps of spaces, and then you essentially just have to do it on all smooth schemes at the same time, and then you get these kinds of operations. If you want to define it solely on the level of abelian groups, then I have to ask that you define it for all presheaps on smooth schemes. And of course, usually you will ask various properties of these operations. So probably they should be additive, and maybe they should be stable or something like that. But yeah, I'm just going to list some operations for you that I'm going to use. So there are two sources operations that are relevant for my talk. And so the first is well, the Voevodsky operations. And well, again, I'm not going to tell you how he does it, but Voevodsky constructs examples of such operations, right? So Voevodsky constructs the following operations. They're called SQI. So they're Voevodsky's version or motivic Steenrod operations. And they go from H star star of, let's say, X, where they have two coefficients. And then they do something specific to the indices. So namely, the first index gets added I, and the second index gets added I over 2, except that's maybe not an integer, so you round it down. So it turns out it does this sort of thing. Well, this is what it does. And of course, then he proves that they have all sorts of good properties. So they satisfy a Cartan formula, which looks more or less like the one in topology, just some taus maybe thrown in, and it does satisfy some Adem relations, taus and some rows. Okay, he studies those. So I wanted to give you an example, which is that if you take I equals 1, right, then this number here, of course, is 0. So it's Q1, the motivic Q1, it just increases the cohomology degree by 1 and leaves the weight alone. And so there's another operation which one knows, which does this, which is called the Barkstein, which you can define in great generality, and it turns out that's the same, right? So this is just the usual Barkstein. But there are many more operations, and there are apparently they're extremely intricate somehow structures on this motivic cohomology. I mean, he used them in an essential way. Okay, so he used them in an essential way to prove the Bloch-Kato conjecture, which I think we can agree is a very, very cool result. And then there is another source of operations, which I think has always been known. Like, I mean, even before Voevodsky's operations, there was always people knew that you could do the following thing, and these are the so-called E-infinity operations. And when nobody's listening and I'm just sort of talking with my friends, and I just call these the dumb operations. So Of course, it's not that dumb, but anyway. So the point is that these complexes, Z, J, if you want with an X there or not, doesn't really matter. They come with coherent sort of multiplicative, coherent commutative multiplications. They have coherent commutative multiplications. And what this tells you is you can just basically use the fact that sort of multiplication is commutative in a homotopy coherent way to extract operations. So the multiplication looks something like this: Zi tensor Zj goes to Zi plus j. Okay, so the multiplication adds the weights. That's clear enough. And so whenever you're in this kind of situation, right? So you look at the map Zi tensor Zi goes to Z2i, and this is going to be invariant under the C2 action on the source, then there's always a standard way that you can construct operations. So this yields, by standard methods, operations which I will call maybe skew-I top. Skew-I top. And what do they do? Well, again, we're going to start with H star star X with coefficients in F2. And they go to H. Yeah, now you do something with the indices. And so somehow the way that motivic homology works is that the first index is somehow the topological one. So it's clear what we're going to have to do. We're going to add I to the first index. That's just always what you do. However, right, so the very intricate thing about the Voevodsky operations is that they change the weights in a sort of not unpredictable way, because I gave you a formula, but they change it in an interesting way. Whereas here, as I said, this arises from the case where this thing here is just I again, right? So it just arises from the map Zi tensor Zi goes to Z2i. So we are always going to land in weight 2i if you start in weight I. So maybe this is so this was not great. 2 star, right? So it will just double the second index. Maybe I should have, maybe let's make this a star prime. So 2 star prime. X comma F2. So it will always do this thing. So sometimes it will have lower weight than the Voevodsky operation. Sometimes it will have higher weight, but it will always be, in fact, it will always be the same weight. Okay, so that's the second source of operations. And now here comes the idea, which I will leave to you to judge if it's clever or completely stupid. But so here's what we call the generalized operations. Yes, I do mean classical to homotopy theory, yeah. Okay. So now let's think about for a little bit what kinds of operations we have, right? So let's say I start at the homotopy class in degree cohomology class. In some degree, PQ, something like that, right? And now I'm asking myself, what new classes can I produce? So, well, it's going to be a very sort of impressionistic picture, but okay. So I'm starting my picture here, and I have some class in some degree PQ, let's say maybe here. This is the original class. Okay, so now what can I do? Well, I can use the Voevodsky operations. So what's the first one? The first one is the Bachstein. So it's going to increase the degree and it's going to keep the weight the same. And the next one is this Q2. So it increases both of them. So now we somehow go to here. And then the next one only increases the degree again. And another one here. And so on. It keeps going, of course. I mean, at some point you get zeros, but okay, so these are the Voevodsky operations. But I could also do this topological thing, right? So the topological thing will always double up my weight. So wherever that is, I guess maybe here. And then we just get more here. So then these are somehow in the same degree in weight. And then this is here, and keeps going. So these are the E infinity operations. All right. And I mean, what you will observe is that somehow, I call them skew I and skew I top, right? So they are somehow close, at least notationally, they're related. So there's some relation between this guy and this guy, between this guy and this guy, this guy and this guy. Then, I mean, these are even somehow in the same degree. And then this guy and this guy, this guy and this guy, and so on and so forth. And so it's already a bit suspicious that they bunch up like this. So you're probably not going to be very surprised if I tell you that, in fact, they differ by a very predictable thing, which is that you multiply by tau in order to, well, increase the weight, right? And so if you want to get from this to this, you multiply by tau. So in this case, the Voivodsky operation divides the E infinity operation. And here you go the other way around. So the Voivodsky operation is a tau multiple of the E infinity operation. So let me write this down. So this, what I said, is only true if you assume that square root of -1 is in your field. So let's assume this for simplicity. But if that is the case, then the purple lines are multiplication by tau, by appropriate powers of tau. Okay, and so what this tells you is that for every I, either sort of the Voivodsky operation can be recovered from the E infinity operation, or the E infinity operation can be recovered from the Voivodsky operation. Or, I mean, sometimes both of them, because they're the same, right? And so somehow what this suggests is that in this range here, the Voivodsky operations are better, and in this range here, the E infinity operations are better. That was your question. Does tau, in cohomology, tau is positive weight. In homology, it would have negative weight. Okay, and so then we just make the following, as I said, somehow a bit ridiculous definition. I said skew I tilde of x. Okay, so this will be either skew I of x, so this was the Voivodsky operation, or skew I top of x, whichever one has lower weight. And I mean, as I just said, let's assume square root of -1 is in k, although we don't need to assume this. In which case, if they are the same weight, then they're also equal. So then it doesn't matter, right? So whichever has lower weight. All right, so that's the definition of our cool new cohomology operation, which will feature in the result that I'm just going to state. And so I want to point out that, I mean, while the definition is very sort of straightforward, this, I mean, it's really quite painful to work with, because it's very unpredictable sort of in what weight you end up when you start with some class, right? So somewhere in the beginning, you keep slowly increasing the weights until you reach some sort of final spot, namely the spot which is twice the weight that you started with, and then you do not do this. And I mean, of course, it's easy to explain in words, but in formulas and in trying to like do arguments and proofs, this is unbelievably painful. But in any case, this is the definition. Okay, and so now with this out of the way, I can tell you what the cohomology of Eilenberg-MacLane spaces is. Well, under some assumptions. So I will quickly remind you about some standard definitions from topology, which feature here. So let's say I have some sequence of integers I, which is equal to I1, I2, and so on, up to some number I k. It's okay. And then I make an operation called skew tilde upper capital I, and it's just you do this sequence of skew tildes, right? So this will be skew tilde I1, and then you do skew tilde I2, and you keep going, and you go to skew tilde IK. And so now I want to, yeah, I don't know why I didn't say this before, but what I want to stress again is that, I mean, sort of the by degree of this operation very much depends on what you stick in. So if you start in some degree PQ, and then you apply this skew tilde I, you get to some new degree. Okay, so maybe you changed it by 5,3. And if you start in some other degree, then it changes by something else. So in particular, these are very much not bistable operations. They are actually stable in the S1 direction, but they're not stable in the GM direction. So maybe I should, right? So not bistable. So these are some kinds of unstable operations. Okay. And then it turns out that some of these sequences are better than others. And so the classical notion is of this of admissibility. We call the sequence admissible if the following happens: if is greater than or equal to times is plus 1. Okay, so the number halves each time. Yeah, so that's correct if I remember correctly. So this should hold true for all s. And then you have something called the excess, so e of I, and it's just going to be the sum of these differences. So the sum over s of is minus 2 is plus 1. Right, so each time this number is bigger than this number, so the difference is non-negative. So you're here adding together a bunch of non-negative numbers, and this is called the excess, how non-efficient you were in ensuring this inequality. And so now I can state the theorem for you, which is that, so I assume that I is greater than or equal to twice j. Well, I haven't told you what I and j are for yet, but you can imagine, right? So then what I will look at is I take the cohomology of the Eilenberg-MacLane space K F2 round brackets J, comma I. Okay, so the degree is bigger than or equal to twice the weight. So the most standard example is always these 2n things, right? So in here is saying you can do 2nn or 2n plus 1n and so on and so forth. And we want to know what is this. And it turns out that the answer is the following, which will look very much like the classical answer, which is that you just take sort of the coefficients, which, I mean, one knows is Milnor K theory at join tau, and then you just make a polynomial ring. And it's going to be a polynomial ring on these skew tilde I of x. Okay, so I need some qualifications here, right? So where, of course, x is the fundamental class, so x will lie in H ij of k f2 j I with coefficients in 2. Well, I guess, well. So this is the sort of tautological or fundamental class. I guess because I defined for you the cohomology of free sheaves as some classes of some homotopy class of maps, right? It corresponds to the identity map under this definition. And of course, so this is going to be a polynomial ring and infinitely many variables. And so this I is required to be admissible. And the excess is required to be less than j. Okay, and so basically, unless I did it wrong, this is exactly the same answer as you have in topology. So if you ignore the second index and if you ignore the tildes, then this is exactly the same. Okay, so that's the statement of the theorem. Any questions so far? Very good, very good. Let me make 2 remarks about this. And the first is that we have this curious condition that I is greater than or equal to 2j. And I mean, I don't like it, but it is necessary in some sense. So let me write, is necessary in general. Because otherwise, one knows that this cohomology actually has tau torsion. So it will no longer be free over the cohomology of the point. Otherwise, the cohomology has tau torsion. Of course, that doesn't mean that like everything is lost. It's just that the answer is going to be more complicated, and I would like to have a good description in general. But okay, so if you want an answer sort of very much like this, then you need to assume I think 2j minus 1 is probably also okay, but it seems more difficult. But certainly as soon as you go to 2j minus 2, you'll already have to take into account tau torsion somewhere. And the other thing which I want to say is that, I mean, the elephant in the room, I guess, is that, of course, Wojewodsky has worked on this. So Wojewodsky has determined the stable answer, right? So Wojewodsky has determined. sort of the stable version, where you take the limit over I and j, I think, of h star star k f2j I. And he found, of course, famously what he calls the motivic spin-mode algebra, which is, of course, exactly spanned by his operations. And so in his paper about motivic Eilenberg-MacLane spaces, he makes this remark that unstably his operations are not enough to span it because, well, somehow sometimes there's slightly mysterious other operations which seem to be relevant. And yeah, I guess we found that the slightly mysterious other operations are the dumb operations. That's the result. Okay, and so now what I want to do for the end is well, there's two more things depending on how the time goes that I want to do. The first is I want to tell you about the analogous picture in homology. So right, I mean, yeah, so I haven't defined motivic homology for you, but let me just say that, I mean, Woiwadzki, he constructs a symmetric monoidal functor from, well, pre-sheaves on smooth K to his category of derived motives. So this is some stable infinity category, dm of K, comma, A or F2. Let me just put F2 here. And using this, we can define the motivic homology. So that's, of course, a very non-explicit thing, but I will go with it. So using this define, for F in, yeah, any one of these pre-sheaves, we can define the motivic homology. H star star of F comma A. Right, so what I mean is that you take some object here, you apply this functor to get into this category, and in this category, somehow you still have bigraded spheres, and so you just look at sort of the homotopy groups of the object there, whatever this is. So for now, I mean, we can just say this is some formal construction. But so there's this functor here being a tensor functor, it gives us a number of good properties, right? So for example, you have this addition operator, right? So cohomology, you can add cohomology classes. So this gives you sort of K of F2ij times K of F2ij goes to via plus to K and the same degree, right? So if you take a class in degree ij and another class in degree ij, you add them together, you end up in degree ij. F2ij. And what this tells you is that if you try to work out the homology of these Eilenberg-MacLane spaces, you get H star star K F2ij tensored with H star star K F2ij goes to the same thing, H star star K F2ij. So this tells you, I mean, of course, very well known, that the homology of this Eilenberg-MacLane space is always going to be a ring. Get a commutative ring for every I and j. But I mean, there's more that you can do, right? So if you take two cohomology classes, you cannot just add them, you can also multiply them. And if you do that, then the degrees add, of course, right? So you get the multiplication K of F2ij times K of F2ij goes to, via multiplication, K of F2I plus primes here, I plus I prime, J plus J prime. And again, I mean, this gives you then something which is happening in homology, right? So so let me write it out maybe once more. H star star of maybe I'll just write K of I comma J because it's getting so long. Tensored with H star star K of I comma J, I prime comma J prime, and it goes to H star star K of I plus I prime J plus J prime. So what I just want to point out is this very well-known fact that on the homologies of the Eilenberg-MacLane spaces, you have a lot of operations in order to combine elements which you had before. So you have the usual product, sometimes called the star product, and then you have this special new operation that I just told you about, sometimes called the circle product. And so modulo the fact that you don't always get the coalgebra without some extra assumptions, this basically says that the homology of all the Eilenberg-MacLane spaces taken together forms something called a Hopf ring. And this is some complicated algebraic gadget, but as usual, when you have very complicated algebraic gadgets, they also constrain a lot sort of what can happen. And so it's useful to use all of these structures. And so what my plan is now going to be to describe to you the homology of Eilenberg-MacLane spaces in terms of these two structures, the usual product and the circle product. In order to do this, I want to write down some generators for this homology. So we need to look in some low degrees where we can work out the homology so that I can give you some elements. So I can use the following facts. So for example, one knows that K Z-mod 2, 1, 1, this is given by something called the étale classifying space of Z-mod 2. So I'm not going to tell you exactly what this is, but the point is that one knows here the homology of this guy and the cohomology of this guy. I mean, in fact, the cohomology is maybe better known, but you can get the homology by dualization. And there's a similar thing, which is that you can use the étale classifying space of GM, also known as P infinity. So this is K of Z1, 2. But this maps, of course, to K of Z-mod 2, 1, 2. And we know this, okay? And there will be two more, namely K Z-mod 2, 0, 1. This is something called in this Nesevich classifying space of Z-mod 2. And again, one knows the homology and cohomology, great. And then you can do the same thing here in weight 0. So there's some B2 Nesevich of Z. This is K of Z 0, 2, and it maps to K Z-mod 2, 1, 2, no, 0, 2. So in each of these four spaces, I know exactly what the homology and cohomology is, and one can use this to write down certain classes. So I'm not going to tell you exactly what they are, but what all of the cohomologies and homologies are, but I'm going to tell you what the classes are. And, probably you know the homology of Eilenberg-MacLane spaces, so all of the names will look familiar. So we can use this to produce elements. So E1 and alpha lower round brackets I and beta lower round brackets I. And so that's what the usual classes are called in topology. And so we will have two versions of these. So ones with a round bracket 0 behind and ones with a round bracket 1 behind. So alpha I1, beta I1. And where do they live? Well, this guy will live in, both of these actually live in H star star K Z-mod 2 0, 1. And this one lives in H star star K Z-mod 2 0, 2. And the other ones live in weight 1. So these live in H star star K Z-mod 2 1, 1, and this guy lives in H star star K of Z-mod 2 1, 2, like this. And they have some weights, which if you want, you can ask me later. But so the point is, these guys here, they always have the same degrees as these guys here. But these guys have weights, and these guys are all in weight 0. So then there's this sort of admissible circle monomial. So let's see. I will set maybe alpha minus 1 equals E1. And I call this monomial alpha I1 circle circle alpha I don't know n, and epsilon 1 so epsilon n circle beta J1 circle circle beta JR delta 1 delta R. So I have some condition when is this guy called admissible? if two things happen. First of all the i's should be distinct. Okay, so somehow these are in some sense sort of exterior classes. You can't have more than one of them. Right, so there's some rule about when you can put zeros and ones. So I'm gonna maybe write it out because why not? So I will, okay, so if alpha I of 0 is involved, then alpha I prime of 1 and alpha, and beta j of 1 are not involved for I prime less than I, and I think j less than or equal to I. And then there's another condition which is sort of similar to this. So I'm not sure that this is going to be super helpful if I write this out for you. But so the point is, what's happening is that in topology, you make these you look at these circle monomials, and you only have this condition that the alphas cannot occur twice. And so what you're supposed to do in motivic homotopy theory is you start with one of these topological monomials, okay, and you put zeros everywhere, and then you get the class in weight 0. Now you don't want the class in weight 0, you want the class in some sort of higher weight. And what you then have to do is you have to turn some of the zeros into ones. I mean, exactly that many ones as you want the weight to be at the end, right? And what this rule is saying here is that you have to do this in a certain specific order. And you can always do this if you start with a monomial with all zeros. There's exactly one way that you can raise the that you can replace zeros by ones and still satisfy this rule, and to move it into any way that weight that you want. And that's what this says. And then with this preparation, I can give you the theorem, which is also, of course, between me and Mike. So again, for I greater than or equal to 2j, if you look at this homology of k z mod 2 j comma I, this is going to be an exterior algebra. Okay, so it's a characteristic 2. So I'm just, if you anything that you square, right? So the generators, they square to 0 on these admissible circle monomials. But I mean, of course, a general circle monomial, it will live in k z mod 2 ij for some I and j, right? So you have to take those those admissible monomials which actually land in the homology of k z mod 2 ij. But I mean, of course, that speaks for itself, right? So maybe off by degree. Okay, so that's the homology version of the theorem, and I'm essentially out of time. So let me just very quickly say some words about the proof. And so somehow the point here is that Voevodsky proved that the motives of these classifying spaces, where again you need this assumption I greater than or 2j, they're just split Tate motives, right? So they're just sums of f2, ij, whatever's. And if you take the topological realization, then you know that you get the standard Eilenberg MacLane space. So basically, you're just forgetting the weights in the topological realization. And so what this tells you is that whatever the answers, either in homology or cohomology, were topologically, it will be the same answer. And you just have to put weights in all the correct in all your generators. You have to figure out the correct weights. And so it's basically just some sort of bookkeeping problem. And so what we do here in some sense is we have a proposed answer for homology. We have a proposed answer for cohomology, which are basically two guesses for what the weights should be. And what it turns out, the main thing which you have to prove is that the two guesses agree. So you get a map from your proposed answer, let's say in homology, to the actual homology, which is the dual of the cohomology, which then maps to the proposed answer for the dual for the proposed answer in cohomology. And if it's going to be correct, then this induced map from two things which you know has to be an isomorphism. And this is somehow saying that the sort of the weird thing in which this Q tildes changed, right? So this unpredictable weight change that you had in this Q tildes, and you have some unpredictable weight change in these admissible monomials here. And somehow when you pair them together, they have to do exactly the same thing. And it turns out that one can prove this. And then everything follows is Basically, it doesn't use anything that Voevodsky didn't already have in his paper. And that's the end.
All right, let's thank Tom.